All right, let's get into it. Today, we're going to build something pretty incredible. We'll start with a toy we all know and love, Legos. But trust me, by the end of this, we'll be talking about the programmable future of medicine itself. So let's dive right in. So let's kick things off with a big, kind of wild question. What if we weren't just stuck with the biological rules we were born with? I mean, what if we could literally hand our own cells a brand new, upgraded instruction manual to fight disease? It sounds like something straight out of a movie, right? Well, guess what? It's happening right now. To really get how this works, we first need to meet the defenders of our body. And honestly, the best way to do that is to imagine your body as this giant, complex Lego castle that's constantly under siege from all kinds of outside invaders. Okay, so patrolling the walls of this Lego castle are your T cells. Just picture them as these tiny little Lego minifigures, and each one is wearing a special little detective hat. Their one and only job is to roam around what we'll call the body playground, find the bad guys, germs, viruses, that kind of stuff, and take them out. They are your personal microscopic security force. But these Lego detectives don't just pop into existence ready to go. They have to go through some serious training first. They start out at this tiny little school called the Thymus. It's here they learn two absolutely crucial rules. Number one, do not attack our own friendly Lego blocks. And number two, definitely do attack the bad guys. It's only after they graduate that they get to go out into the big playground, which is the rest of your body, to actually do their job. And it's not just one type of detective, it's a whole team, a whole crew. You've got your killer T cells, think of them as the brave Lego knights on the front lines, fighting invaders face to face. Then you've got the helper T cells, who are kind of like the Lego cheerleaders, sending out signals to call for reinforcements. And finally, you have the memory T cells. These are the Lego librarians who keep a photo album of every single bad guy, so if one ever shows up again, the team is ready to go instantly. But what happens when the bad guy isn't an invader from the outside, but a traitor from within? Something like cancer. See, this enemy is way sneakier. And our standard Lego Knights, well, they often can't even see it. So to fight this battle, our heroes need an upgrade. They need superpowers. And this is where science steps in with an incredible real-world technology called CAR T-cell therapy. The easiest way to think about this is that we're taking our normal T-cell minifigures and we're giving them a custom, high-tech helmet. This helmet, it's like a pair of supervision goggles, and it's been genetically engineered to see one thing and one thing only: cancer cells. But here's the thing, just giving them supervision isn't quite enough. Fighting cancer is exhausting work. Our T-cell heroes get tired out, so scientists needed another tool. A way to go in and rewrite the T-cell's internal instruction manual. Think of it like a magic remote control for their DNA. Now, this remote control, which is based on CRISPR technology, it basically has two main buttons. You've got the red CRISPR off button. That one can find certain instructions and just silence them. For example, it can find the gene that tells a T-cell, hey, you're getting tired, and just switch it off. Then you have the green CRISPR on button, which does the exact opposite. It can activate new instructions, like turning on a gene that tells the T-cell to shout for backup even louder than before. So here's the game plan, how they actually build this tireless warrior. Step 1, scientists pinpoint the exact genetic instruction that makes a T-cell get tired, that sleepy gene. Step 2, they use that magic red button, CRISPR off, to simply switch it off. And step 3, the result is, well, it's incredible. You get a superpowered T-cell that can fight cancer relentlessly without ever needing to take a break. Okay, so we've had a lot of fun with the whole Lego analogy, right? But now we're about to make a huge leap. Because it turns out, this whole process of reprogramming cells, it's so much more profound than just giving minifigures new hats. It's a complete paradigm shift in how we even think about biology itself. And this is where our simple little Lego story gets a massive, and I mean massive, upgrade. There's this quote from the source material that connects what's happening inside a cell to this really powerful concept from the world of software development, infrastructure as code. Now that might sound super technical, but stick with me, because this single idea, it reframes everything. This translation table right here, this is our Rosetta Stone. Let's break it down. In the tech world, a server is the basic machine that does the work. Well, in our new analogy, the T-cell is the server. That CRISPR edit we just talked about, that's the configuration file. It's literally the code that tells the server how to behave. When the T cell sends out those backup signals, it's acting just like a microservice, a little program that sends messages. And maybe most amazing of all, the cell's ability to pass these new instructions down to its children, that's like a Git repository, a system that saves the code and tracks every version to make sure every new copy is perfect. So let this sink in for a second. What this all means is that scientists aren't just tweaking a single cell anymore. No, they are installing a complete automated system, what software engineers call a pipeline, directly into our biology. They're writing biological code, they're deploying it, and they're creating a system that can run, multiply, and even update itself. This is what that biological pipeline actually looks like in practice. You define the cell's behavior as code using CRISPR. The cell's own memory system acts as version control, making sure those changes stick around. When the cell divides, the deployment is perfectly consistent. Every new baby cell gets the exact same programming. And the whole thing scales on demand, multiplying into an army of programmed warriors to fight off a threat. Which brings us to this absolutely breathtaking conclusion about where all this is headed. We are entering a brand new era, an era you could call BioOps, where the core principles of software development and operations can be applied directly to living, breathing biological systems. I mean, we've gone on quite the ride today, haven't we? We started with a simple Lego castle. We met our T-cell defenders, gave them super goggles and a magic remote control, and we ended up here. This is the ultimate reframe. We are moving from being passive observers of biology to becoming active engineers who can actually program it with code. This last quote just ties it all together perfectly. Our T-cell, which we can call Tom for our story, is no longer just a simple biological piece that just feels and responds. Through this incredible technology, it has evolved. It is now an agent that can be programmed to deploy its own functions, its own infrastructure, all to achieve a specific goal. And that leaves us with this final question, one that's both thrilling and, let's be honest, maybe a little bit terrifying. We have unlocked the ability to write code for living cells. Cancer is just the first application. Now that we have this power, the question is no longer can we program biology, but what should we, and maybe more importantly, what shouldn't we program next?